Welcome to This Explainer. Today, we're taking a really close look at one of the most fascinating and frankly cunning cellular infiltrators in the entire natural world. We're talking about Listeria monocytogenes. Now, named in honor of the infectious disease pioneer Joseph Lister, you might think this is just your average run-of-the-mill bacteria trying to fly under the radar, but no. This microscopic mastermind does something completely counterintuitive. It actually actively seeks out the very immune cells that are specifically designed to kill it, and then it breaks in on purpose.
Okay, let's dive into this because this is the absolute central paradox of our explainer today. The macrophage is basically the heavy artillery of our immune system, right? It's literally built to efficiently kill, clear out, and digest bacterial invaders. So how on earth does a microbe not only survive but actually thrive inside the exact immune cell built to destroy it? To really understand this, we have to look at the bizarre double life of this rod-shaped bacteria. I mean, one day, Listeria might just be chilling out in nature, sitting quietly on a blade of grass in a field. But the very next day, it finds itself inside a mammal, actively being devoured by a hostile macrophage. And what's truly amazing here is its profound adaptability. Through eons of trial and error, it has evolved to perfectly command both of these wildly different environments. It's wild! Which naturally brings us to Phase 1, the Great Cellular Jailbreak. First things first, we need to define the battlefield. When a macrophage encounters a microbe, a section of the macrophage physically surrounds the bug, disengages from the rest of the membrane, and pulls it inside the cell. This creates a structure known as a phagosome. You can think of it as a tiny, membrane-encircled jail cell that the host sets up specifically to trap and encase invading microbes. This is ground zero. So let's walk through exactly how this breakout goes down. Step 1. The macrophage swallows the microbe. And Step 2, our phagosome jail cell is formed. Now, Listeria just waits. Because, why waste energy making proteins for the outside world when you're trapped inside a cell? Instead, an absolutely crucial protein called PRFA acts as a trigger to essentially unzip and release about 15 previously suppressed genes. This newly produced substance, called listeriolysine, then literally breaks down the walls of the jail cell. Boom, escape. But you might be wondering, how does the bacteria actually know when to pull the trigger? Well, mammalian cells, unlike the environment outside, are super rich in a substance called glutathione, and they run at an elevated body temperature. These two factors act as incredibly specific chemical and thermal triggers. So when it's exposed to glutathione and body heat, that PRFA protein we just talked about acts like a zipper, unleashing the genes that create our breakout tool, listeriolysine. Now, the host cell isn't completely defenseless here. It's got some extreme backup plans. If it senses trouble, it can deploy lysosomes, which are these digestive vacuoles that clean up the cell through a process called autophagy. Or it can initiate apoptosis, which is programmed cell self-destruction. Using destruction enzymes called caspases, the cell will literally hit the self-destruct button. It chooses to sacrifice itself rather than become a pathogen factory. But here is the absolute genius of Listeria. The listeriolysine acts so incredibly fast that it breaks the phagosome jail cell before these deadly lysosomes can hook on, and well before the self-destruct sequence can even finish. And with the jailbreak complete, the organism initiates Phase 2, hijacking the host's machinery. And this brilliantly illustrates its stealth capabilities. You see, out in the open environment, Listeria uses these tail-like structures called flagella to move around. But inside the macrophage, it shuts flagella production completely down so it doesn't get detected. Instead, it physically hijacks the host cell's own actin proteins, basically using them like little outboard propellers to glide right through the cell. This allows the bug to shoot directly from one cell to another without ever going outside, completely avoiding the broader immune system. It's a total phantom. This remarkable adaptability extends to temperature too, in a very practical and honestly slightly alarming way. Listeria doesn't just survive in cold refrigerators. It actively multiplies in them. A piece of cheese with just a few organisms can become heavily contaminated if you leave it in the fridge for a couple of weeks. Yet at the exact opposite end of the spectrum, at high mammalian temperatures, it shuts off that flagella production to become non-motile. And because it colonizes mammalian bowels, kind of like E. coli does, it ends up contaminating dairy, lunch meats, and produce via fecal waste. Which naturally brings us to a massive plot hole, right? If Listeria is so incredibly common in our food supply,
And it's such a master of cellular infiltration. Why aren't more cases seen clinically? Why are there only about 1 to 2,000 serious cases reported annually in the entire US despite how abundant this organism is? Well, the answer is actually quite simple. Our everyday exposure risk is much lower than it seems because not all strains of Listeria monocytogenes are created equal. Out of the 13 recognized strains, only 3, specifically strains 4B, 1/2A, and 1/2B, are actually pathogenic for humans. So if we do happen to have Listeria in our food, the overwhelming odds are that it just isn't one of the dangerous strains. Furthermore, you have to look at the massive infective dose required to actually get you sick. 10 million, roughly 10 million bugs. You see, Listeria is highly susceptible to acid. It dies if the pH drops below 5.5. Since normal human stomach acid is much lower than that, you'd literally have to consume a truly staggering quantity of the bacteria to ensure that even a few survive the stomach. The big exception here, of course, is if a patient has artificially reduced their stomach acid by taking antacids. So what happens when the perfect storm actually occurs? Let's move on to phase 3, the targets and the cure. Usually, an intact immune system with uninfected macrophages and signaling proteins will hunt down and dispose of these infected cells. But vulnerable populations are at severe risk. Listeria has this frightening affinity for the placenta, meaning pregnant women in their third trimester and their unborn babies with undeveloped immune systems are highly susceptible. Once it attaches to the placenta, wandering macrophages have a really hard time dislodging it. It also aggressively targets the central nervous system, making meningitis a very common and dangerous outcome for the elderly and anyone with a compromised immune system. But fortunately, there is a cure. Once diagnosed, which is usually done by testing a blood or spinal fluid culture, listeriosis is highly treatable. Because it is a gram-positive bacteria, it's incredibly susceptible to the penicillin or ampicillin class of antibiotics. As long as the diagnosis is made early and antibiotic therapy is started promptly, the prognosis is generally very good. So, the crucial point is that we're dealing with an incredibly adaptable, potentially lethal pathogen that has evolved to perfectly outsmart our body's primary defenders. But guys, the story doesn't end there. Let's move to phase 4, which is the ultimate plot twist in our explainer today. Because of its absolutely unmatched ability to break into human cells and evade the immune system, scientists are actually turning the tables. They are taking attenuated or weakened strains of Listeria and loading them up with anti-cancer molecules. They are literally using this cellular jailbreaker as a Trojan horse. The bacteria naturally infiltrates the tumor cells, bypassing all their defenses, and delivers a fatal payload directly inside to destroy the cancer. It's a breathtaking twist of fate. I mean, could one of nature's most cunning, destructive, microscopic masterminds actually become our greatest weapon against cancer? It entirely changes how you look at the microscopic world around you, and honestly, maybe even that leftover cheese sitting in your fridge.